Hello everyone, welcome to my shop. I'm Robin. Today I'm going to be showing some grinding tricks on using a spin fixture and aligning a little part. A lot of little details that might be helpful. So let's get to it. Here's our little pieces. These are A2. They have a counter bore in them for an M3 screw with a reduced diameter head. And these are currently straight, made from 1/4 inch diameter drill rod and then vacuum hardened and tempered. And here's one that I've ground, and these need to be ground with a 1/1000 diametric taper over the length of these. So I have my spin fixture sitting here tilted at that angle, so that part is taken care of as far as the taper. No magic there, other than I putting it in the vise and just tilting it in the vise as opposed to putting it on a sign plate and fooling around with that. Vise is quick, and you can tap it in to get exactly what you need as far as taper. One thing I've done to this spin fixture is I've taken a screwdriver, a Ryobi screwdriver, and taken all the guts out of it and just made it basically just for this. Put a mount on there where they can be removed from the spin fixture if necessary. There's an actual bearing in here that actually takes the radial load that's on the pulley so that it's not on this, and that little hex you see there is actually going into the hex drive, and that's what's driving. So this pulley is not pulling on the drivetrain, but it is using the natural reduction that is in the in this drill driver, and it does have a 2-speed gearbox. Pulley made to replace the actual crank that's on there, and a heat sealable urethane belt that's from McMaster and just heat sealed for that distance. Down here I'm driving it with a variable voltage DC power supply that lets me just use the button here to control my speed, so it allows me to just rotate that thing around for indicating purposes without any trouble. So here's the spin fixture, and I have a piece in here that's also 1/4 inch diameter, hardened. It's been drilled and tapped, M3 in the end. And what I have on here is an actual inner race of a 1/4 inch bearing. And I've ground a solid through it with a Dremel disc. But this is a snug fit on here. It's very grabby, and you'll see where I'm going to use that to rough align the piece. One thing that is very important with V-block work, and that is to realize that when you're clamping things, there's always distortion. Doesn't matter how lightly you clamp, whatever you're doing, things are moving. So one of the things you can do to help this V-block and this part actually run straight, such that this axis is parallel to the axis of rotation, is to use a very thick backup block so that you're putting a uniform linear pressure over the entire surface, and also such that it's actually touching with the length of the V-block. If we come up here and look at the V-block, we see that this is relieved in the back, and that's where the V stops down here. Also, having the screw centered axially between the distance here of the engaged V-block is important. If you move that screw to the front, it will tend to tilt this piece downhill. If you move it towards the back, it will tend to tilt this piece uphill. So every little nuance there is extremely important when you're down in the 10th and sub-10th work. You have to think of all these things as being rubber and responding that way. So this is indicated in to run reasonably true. This face on the end has been ground with the edge of the wheel such that it's running true. So the facial run out of this is minimal. It's just whatever bearing run out is in this head. So this face is running very true because it is the only reference that this part has. This part's going to be screwed on there with a screw, and that interface right there is what's actually holding that part true. So this OD really isn't all that important because I'm going to be indicating these individually and showing you the techniques, and one of the special things that's very important in doing this. Since we're expecting this part to be able to translate on that mounting surface smoothly in very small increments, 1/10 increments, this original as turned face, we have to be very careful to get rid of the turning marks and any burrs or nicks or anything that are on there. So these have been, I have taken these and just given them a good hit on the precision ground flatstone. And basically what that's doing is putting a gauge block type finish on the face there that can easily translate. You can see the shine on there. It got rid of all the burrs, and that will be able to easily move on the mounting face that we're bolting up to. So anyone who's ever done any mounting of something like this using a screw to mount something and tap it in and then tighten the screw to hold it tight will tell you that it doesn't work as well as you'd like, because the irregularities on the shoulder of the screw, the irregularities on the counter bore, how perpendicular or parallel they are when it clamps up, all means that when you go and give this, you've gently tightened it, you tap it all in, and it's running in 50 millionths, and then you go ahead and tighten this as tight as you would tighten it to make sure that you're going to be safe to grind, and it moves, it pushes it off center, and you can just about guarantee the number of times that it's not going to do that is just isn't going to happen. So this is the piece that is part of the magic to put in your tool room arsenal, is when you have something like that you need to have not move when you're indicating, you make this intermediate piece, and this goes in and acts as a counter bore. The longer M3 screw passes through. I have this distance here is just for grinding wheel clearance. The knurl is so that what I'm doing is when I go to tighten this, after I've already snugged it, when I go to tighten this, I resist the torque I'm applying with this hand with my fingers here. So I'm actually going, I'm twisting, counter twisting, such that there's no relative motion between this and the part. Therefore, there's no, nothing scuffing this around trying to push it around. It's pure axial force. And I've done 50 or 60 of these with this way, and this basically does not move. I've tightened every single one of them that way, and they stay right where it's indicated. So I'm going to demonstrate that on the piece here. Clean my part surface, clean my arbor surface, put the screw through the whole assembly, slide my ring up until I start to engage my part. Try and do this where my fingers aren't in your sight. I'm just sliding up onto the piece. The part is a little bit bigger than the arbor, so I don't want to slide up too far. I just want to get enough where I'm just basically aligning those pieces and just putting the gentle pressure on there, just enough that it stays put as I indicate. Now I just drive right onto the indicator. I don't have to move. The indicator is sitting where it needs to be, and it stays there for all the parts. And now I'm going to just zoom in a little bit here closer so you can see the indicating a little bit better. And I'm using my voltage knob down here on the bottom just to drive this, find my high and my low. Stop on the high. Try to go roughly halfway. A little bit high there. Probably went too far. I did a little bit there. That's about a tenth. Now the magic is to hold this, counter torque with these fingers right here, my left hand fingers, as I tighten with my right hand fingers. What I'm doing is I'm keeping this from rotating whatsoever. The screw rotates on here. I'm absorbing the torque, the drag torque between the head of the screw and this transfer part between my hands, so that's why there's no relative motion happens to the part. Now if I've done it well, this should be still within a tenth. Got exactly what it was. Okay, so that's this can be all different forms. This just happens to be the form that works here. But the idea of having something where you can hold it still so that as you tighten you get no relative motion, no rotary motion between the mounting face of this and the part is what lets you indicate this in. Now this I have such that I can now drive. Don't have to touch the indicator, don't have to move it. It can stay there through all the operations. Now I just drive here, and I'm going to fire up the grinder, and we'll just show the grind. I'll zoom in here. And I'll just show you the grind where we just go in tangential. I don't have to traverse sideways, I don't have to do anything. I'm going to fire up and I'm going to drive under there. Turning the rotation on. Now I'm just going to drive in, and you'll see the grind start to progress from the end because of the taper, and as I go deeper in till I'm at the low point, the grinder's been off a little bit, so it's climbed a little bit. Now I'm just going to feed down until that cleans up across there. That little bit of variation you see is actually that little bit of residual run out, that tense that was there. And when that's done, sparking out, I just drive out. You can take a look at what it looks like run out wise here, where we've ground. And this is now the run out that's there, just the residual run out of the grind head. So the several points, just reminder of what we're showing here. One is having the indicator and the grinding wheel all in the same location, such that I don't have to move that indicator at all from part to part. The part to get any torsional motion on the face of the part to be strictly absorbed by the screw between my fingers and this knurled ring. That's why it's got a nice fine diamond knurl on it. The sleeve, springy sleeve that'll slide over to get me in the ballpark, so I don't have to tap it around, a mile. And that's it. So I just thought that might be of interest to you guys, and see some techniques for being able to tweak something that you're mounting with a screw.